All right. This is potential energy functions, and it's quite honestly, is one of the most exciting things you learn in physics C, in my opinion, because it is a gateway into quantum mechanics. Okay, when you get to quantum mechanics, you'll learn about things called the infinite square well, and this is kind of a precursor to that. Now, is it super heavy on the quantum? Not really. Okay, but this again, like I said, is a precursor to things like that. Okay, so potential energy functions. Really quickly, I'm going to talk about stable and unstable equilibrium, but I need to talk about equilibrium. Okay, equilibrium is where the force is equal to zero. The net force is equal to zero. Okay, and since force is equal to negative du over dt, okay, which is something that we learned in the previous section. Okay, I actually haven't made the video for the previous section yet as of the time of recording this, so maybe it doesn't make sense right now. Okay, this would say this is where slope, okay, of u u versus t is zero. Okay. Okay. Stable equilibrium. Okay. Stable equilibrium is a minimum in the potential energy function, which we call u of x. Okay. The object, okay, wants to stay at stable equilibrium. Okay. Moves towards it. Moves towards. Okay. Stable EQ. Okay. Um, and it's like, I mean, like humans, right? We move towards stability, right? We don't want to be unstable, okay? But some of us end up doing that anyway. Maximum. So a unstable equilibrium is a maximum in the potential energy function, okay? And the object, okay, wants to move away, okay, from equilibrium, okay? Object wants to move away from equilibrium. Okay, so if you remember in E&M, when we did the E&M intro, we talked about contour maps or electric potential lines and stuff like that, and the object moves towards lower potential. That's exactly what the case is here. If you set a marble on the function, where is it going to go, right? So think of like the stable equilibrium or like as like bowls on the function, and unstable equilibrium as like hilltops or maybe like bowling balls or something, where if you put the marble on top of a bowling ball, it's going to roll off the bowling ball, right? But if you put a marble in a bowl, it's going to roll into the bowl, okay? Here's an example of a potential energy function. This is what it looks like, okay? There's a lot of stuff going on here. Don't freak out. But you have a particle mass m, 2 kilograms, has this potential energy function. So this is the potential energy function that's defined for this object or this particle, okay? X is in meters, U is in joules. The following graph is a sketch of the potential energy function. There it is, beautiful, okay? The energies indicated on the vertical axis are evenly spaced, so right, these have all equal spaces between each other. The energy E1 corresponds to the potential energy at position X1, okay? And then E3 corresponds to X3. There is no E2, so don't freak out about that. E2 is more something that we're going to do a little bit later when we do total energy, okay? Determine the numerical values of X1 and X3. To figure out the values for X1 and X3, okay? This is going to be, and these, by the way, right? If you, let me move it down a little bit. Let me move it down so you can actually see the function as well. These are both actually equilibrium points, okay? Because you notice that the slope momentarily is zero, okay, at both of these points, okay? So if I write down my potential energy function, okay, equals 3 x minus 1 minus x minus 3 cubed. I'm just rewriting what I had there. Okay. What I can do is I can actually take the derivative of it. Okay. And if I take the derivative, so I would get du over dx. Okay. This ends up being, and you actually can chain rule this. So when you chain rule it, you'll notice that your interior on both terms, your interior derivative is actually just going to be 1, so it doesn't even really do anything. Okay, so this would be 3 minus, and the 3 comes down 3 times x minus 3 to the second power. Okay. Okay. And then all we got to do, okay, is if we take this is the derivative, right? If I set this equal to 0, I can figure out my stable or unstable equilibriums. So what I'm going to do is I'm going to set this equal to 0. So 3 minus 3 parentheses x minus 3 cubed, or sorry, squared equals 0. Okay. If I subtract 3 from both sides, I get negative 3 x minus 3 squared equals negative 3. Get rid of the negatives because they're both sides are negative. I can cancel them out, and then divide by the 3, and I end up getting x minus 3 squared equals 1. Okay, and it's important to note that when I square root both sides, the 1 can be positive or negative. Okay, so it'll be x minus 3 equals positive or negative 1, and this is actually where we get our 2 points. Okay. So if you look at this, right, and you add 3 to both sides, this becomes x equals 3 plus or minus 1. And then you see you get 2 results from it. Okay? You get x equals 4 if you add, and x equals 2 if you subtract. These are actually both of our equilibrium values. Okay? Um, And the 4, right? 4 is further along the x-axis, so this is going to be the x sub 3. This is going to be x sub 1 right here. Okay, so those are our positions. Now, are they stable or unstable? Okay, x1 is stable because you notice it's a dip, it's a minimum. Okay, x3 is unstable because it's a maximum. Okay. Okay, and then describe the motion of the particle if its total energy is E2 when it's at x equals negative x equals 1, x equals x1. Okay, what happens with the particle is that it oscillates, okay, about the 2 points, okay, where u of x graph, okay, intersects the total energy line. Okay. So let me show you what that might look like, okay? If I take my potential energy function up at the top here, and let's say it says the total energy is E2, so what I'm going to do is I'm going to draw a horizontal line from E2. I'm going to try my hardest to make it horizontal, okay? That doesn't look very good. I was kind of sitting at an angle when I did that, so I probably didn't make a line super great, okay? That's probably a little bit better, but not super great. Then what's going to happen is you're going to notice that if you put an object in the equilibrium, okay, it's going to basically oscillate back and forth in this little bowl, okay? It's basically going to oscillate back and forth in the bowl. It cannot leave this, it cannot exceed where this horizontal line intersects the function because it doesn't have enough energy to do so. Okay, it cannot leave. It's confined in this little bowl. It's trapped. Okay, it can't leave that. Okay, because it doesn't have enough energy to do that. Okay. What is the particle speed at x equals x1 if its total energy is 40 joules? Okay, well, in order to figure that out, I need to use my work energy, or I need to use my conservation of energy, right? The total energy is kinetic plus the potential, okay? If it's 40 joules, if the total energy is 40 joules, okay, then, oh, and sorry, this, by the way, is x equals 2, okay? Because we already solved that from earlier. So I need to figure out what's my potential energy at, right? So, oh, sorry, let me actually scratch that out. My total energy is 40, okay? I set that equal to 1/2 the mass, okay? The mass of the particle is, where is it? 2 kilograms, okay? 2 kilograms, okay? The Oh, sorry. And then the velocity of the particle, we don't know. We're trying to figure that out. And then I need to add to that the potential energy at x equals 2. Okay, well, all I got to do is go back to the potential energy function to figure that out. Okay, at x equals 2, which is x sub 1, that is going to be E1. Okay, which I am not given what E1 is unless I'm tripping. Okay, or I guess what I actually could do, right, is take my potential function and plug in, what was it? Is that 2? Okay, so that would be 3 times 2 minus 1 minus 2 minus 3 cubed, and that should give me 3 minus, this is going to be negative 3 cubed, is, or sorry, negative 1. Net cubed is going to be still be negative 1 minus negative 1, so it would be plus 1. Okay, and that should give me 4 joules of potential energy. So there's 4 joules of potential energy at E1. Okay, that represents 4. Okay. Sorry, some of my pens got caught under the paper there. So I should have 4 joules of potential energy right there. And I've got everything except for my unknown, which is velocity, which is great because then I can actually start solving for things. Subtract 4 from both sides to get 36 equals that. By the way, it's just going to be 1, so it's v squared. And I should see that v is going to be equal to 6 meters per second. Okay, that's all I got to do to get that. Okay, I did have to solve for the potential energy function at 2 meters, but that's fine. Okay, it's important to note, okay, that so when I do this, right, what I can do one of two things. I can take my force function and see what that graph looks like, okay? But I also should understand that the force is equal to negative du over dx. Okay, the negative derivative. So if I know the slope, right, is the slope positive? Is it increasing, decreasing, right? Then I can actually figure out uh, uh, the force on it, right? So for what it should look like is that, right, these are points where it should cross. Okay, here it is at 1, this is at 2, this is at 4. Okay, what it should look like is kind of like this. Okay, it should look something to the extent of this, like a parabola that opens upward. Now it's important to note, okay, that in this first segment right here, the slope is negative, so that's why it's decreasing. Okay, the slope here, okay, is positive. Okay, and then for this last segment, the slope is negative again. Do you see why this is flipped, right? You're thinking, wait, but the slope here should be positive, right? Well, wait, you're thinking, okay, well, if the slope's negative, then the graph should be negative. No, it's because it's the inverse of the derivative, okay? It's the negative derivative, okay? So if your slope is negative, then the graph would actually be positive, okay? Because the value of that function would be positive. Okay, particles released from rest at 1/2. That, by the way, is just x equals 1 meter, and then this we already said was x equals 2 meters. Okay, it's released at rest from 1/2 x1. Find its speed as it passes through x equals x1. Okay, so all I got to do is use conservation of energy, k sub I plus u sub I equals k sub f plus u sub f. Okay, I need to figure out the potential energy at both points. Okay, so what I'm going to do, okay, to get what the potential energy is at both points, okay, is let's see. It's released from rest here. Find its speed as it passes through there. I need to figure out how much of my energy is potential here. Okay, I'll see if I how much of my energy is potential here. So I'm going to do 1 of this should be oh gosh, 1 right there. Okay, u of 1 equals 3 parentheses 1 minus 1 minus 1 minus 3 cubed. Okay. This whole part right here, this whole first term, this is a 3 right here. You probably can't tell. This is just 0 because 1 minus 1 gives you 0. Okay. So then u of 1 would have to be equal to, this would be negative 2 cubed, which would be -8, and then the negative on there turns it positive, so it would be 8 joules, okay? Is 8 joules. So initially, right, we don't have any kinetic energy, but we do have 8 joules of potential energy, okay? The final kinetic energy is 1/2 mv squared, and then the final potential energy, so as it passes through x sub 1, okay, it should be, let's see, this should be, okay, u, okay, of the u of 2, right? I already solved this earlier. Okay, this is 3, 2 minus 1 minus 2 minus 3 cubed. I solved this earlier. It ends up being 4. Okay, so this becomes 4 joules. Okay, now I know everything in here. This is going to be 8, 1/2 times the mass of the particle. What's the particle? It's 2 kilograms. That's just going to be 1, so it's going to be v squared plus 4. You should see that what happens here is when I subtract the 4 here, this becomes v squared equals 4, and you should see that v is going to be equal to 2 meters per second, okay? Now, this is kind of a lengthy potential energy function question, but it's not as bad, okay? It's not too bad. The other potential energy function questions are a lot simpler, okay? So don't be too daunted by something like this being really, really crazy. It's not all that bad, especially when we look at some of these questions. Okay, this is, oh, look at that. It's like Nike, okay? It says just do it, okay? All right, we got this right here. I hope you're not getting like ASMR of me drinking every time I take a drink of water. Okay. Object of mass m equals 0.3 kilograms, part of a system subject to only conservative forces, so that means that energy is conserved. Potential energy of the system is given by this function right here. That's a funky looking function. X is in meters, U is in joules. Graph of the function is shown here. Okay. So what's the lowest amount of mechanical energy the system can have? Okay. Well, let's see. If assuming the object is at rest at x equals 3, okay? So if object is at rest at x equals 3, then -6 joules is the lowest, okay, amount of energy, okay? Or I should say mechanical energy. Okay. Okay. All right. The object is released from position at, is released from rest at position 1.5 meters. The object then moves in the positive direction and later reaches x equals 6 meters. So here's what's important to note. Okay. Object is released from rest at x equals 1.5 meters, moves in the positive direction. Later it reaches 6 meters. Okay. So what's important to note here, let's see, it says explain how the object's speed changes as it travels from 1.5 to 6 meters. Okay. So it's important to note how the function trends at each of those moments. I'm actually going to use a purple pen here to show you that, let's see, at 1.5, okay, 1.5 is right about there, okay? And what you should notice, okay, is, okay, you got this right here. This is where you start, and then it passes at 6, okay? Now, it actually, see, and then later reaches 6 meters. It actually shouldn't go past 6 because, again, you can only go up this high, right? It's basically constrained inside the bowl here, okay? Now, how does it work? Well, you hit the minimum of the potential function right here, okay? So what should actually happen is the speed should actually be increasing because your potential energy is decreasing, right? It's increasing in the negative direction, okay? It's getting smaller, so you should actually be getting faster here, and then you should be slowing down on this segment. So speed up, okay, and then slow down, okay? So okay, from x equals 1.5 meters to x equals 3 meters, okay, speed increases, okay? because u of x decreases. Okay? From x equals 3 meters to x equals 6, speed, 6 meters, sorry, decreases. Because your potential energy is increasing. Okay? So if your potential energy increases, then you have to be moving slower, right? Because then more of your kinetic energy is getting turned into potential. Okay. How about the acceleration? Well, it's important to note that acceleration, okay, accel depends on force, okay, which is slope, okay, or which is, I guess, negative slope. Sorry, negative slope of u versus x. Okay. So from x equals 1.5 meters to x equals 3 meters, okay, you should notice that what's happening, we're doing magnitude and direction, okay, you should notice that for the first segment, the slope is negative, so that the slope is negative and it's getting flatter. So it should actually be rightward and decreasing. Rightward, because that rightward is the positive direction, even though the slope's negative, right? Remember, it's the negative derivative. So it would be negative of negative is positive. So rightward and decreasing because it's getting flatter. Okay? So is rightward and decreasing. Okay, from x equals 3 meters to x equals 6 meters, okay. Oh, I didn't write like a complete sentence, but I don't care, okay. I think you understand how it works, okay. From x equals 3 to x equals 6 meters, it is leftward, because the slope's getting positive, so it has to go in the negative direction, leftward and increasing, because it's getting more steep, okay? If the object is released at position x equals 4 meters with an initial velocity of 10 meters per second in the positive direction, okay, we can figure out what the here. I'll just show the graph here. Okay, so here's the graph and the key here. Okay, what I did here is that if it's released at position x equals 4 with initial velocity 10 in the positive direction. Okay, x equals 4, initial velocity 10 in the positive direction. Then I need to figure out the potential energy at 4, which is -5. Okay, so when I start writing stuff down here, okay, u of 4 is equal to -5 joules, okay? So that means that the total, okay, energy has to be the kinetic energy plus the potential. So that would be 1/2 the mass of the particle, which is given to me as 0.3, okay? The velocity of the particle, the initial velocity is 10, okay? And then -5 to get the total energy of the whole system. Okay, so total energy would have to be equal to this whole thing right here, which is going to be, oh, sorry, that should be squared right there. Okay, this is actually going to end up being 15 minus 5 joules, which is just 10 joules of total energy. Okay. So then I need to figure out if the total energy is 10 joules, then I need to figure out two places on the potential energy function where 10 joules is where it is. And I'm getting right here, and I'm getting right here. Okay? Right? And you can see I already have it marked. So it must oscillate between 1 and 9. Okay? So object, okay, can go between x equals 1 and x equals 9, okay, where all energy is potential. Okay. Okay. Oh boy, right? Gosh, we're having so much fun with potential energy functions, okay? There's two more examples, and one of them is very similar to one that's on your homework, okay? This is very much the same thing, Okay, I think it's actually asking you the exact same questions too. If the total mechanical energy is 10 joules, what are the constraints? Okay, on the object's position. Well, okay, if the total energy is oh sorry, that's negative 10 joules. Sorry, the negative kind of got cut off right there. If it's negative 10 joules, then I'm going to draw a horizontal line at the negative 10, and the particle must oscillate within the little bowl here. Okay, so must oscillate between, okay, x would have to be about equal to, this should be about 1.2, okay, and x would be about equal to 5.8 meters, okay? And those are just estimations based upon where that intersection occurs, okay? So it's going to oscillate between those 2 points. It's probably not exact, but it's not a huge deal, okay? Okay, you could figure out the exact numbers if you plugged in into the equation, but that's too much work, okay? What about the entire interval? So as it goes from 3 to 10, okay, where's 3? 1, 2, 3. So here's my interval on, here's my 3. Okay, I'm gonna mark it in red here. Okay, as I go from 3 to 10, okay, how does the speed change? Well, do you notice that the slope is positive the entire time? Okay, it's decreasing. The magnitude is decreasing. So we're talking about the speed. Okay, the speed should actually be decreasing because your oh sorry, I guess I was thinking of force, but the speed should be decreasing because what's happening is your potential energy is increasing. It's climbing. So speed decreases. Okay, the entire interval. Okay, x equals 3 meters to 10 meters, okay, because u of x is increasing. Okay, so there's less to share with the kinetic side. Okay, and then from 3 to 10 as well, so positive slope, the whole thing, or I should say, slope is positive entire time. Okay, so acceleration is always leftward. Okay, on that interval. Okay, from 3 meters to 5 meters. Okay, magnitude of A increases because it's concave up. Okay, and then from 5 meters to 10 meters. Okay, magnitude of A decreases. Okay. Okay. And then finally, the object is released at position x equals 4. So another problem just like this, just like in the previous one we did. Okay, with initial velocity 2 meters per second to the right, I need to figure out the total energy. That's step 1. Okay, that should always be your step 1 here. Okay, so to figure that out, right, I'm going to do the total energy. Total energy is equal to the kinetic energy plus u at position 4. That's going to give me, u of 4. I can calculate that. I can show it to you right here. When u is equal to 4, okay, then I should get right down here, which is about negative 16, okay? So it's going to be negative 16 joules, okay? That's going to give me 1/2 mv squared plus, or sorry, this will actually be minus 16, okay? Okay, and then calculate everything out. 1/2 the mass of the object is 4. The velocity we're given is 2. Okay, sorry, I'm making a huge mess here. And the total energy you'll end up getting is negative 8 joules. Okay, so the object, therefore, okay, must stay between, it must stay between where the energy is negative 8. So I'm going to look right here. Okay, negative 8 right here. Must stay between about, what's that, 1? And this is about like 6.2 maybe. Okay, so between x equals 1 meter and x equals 6.2 meters. Okay. Okay, and the last potential energy example right here. But yeah, that's the last potential energy example. Is this one? This one actually looks very, very similar to one that's on your homework, I believe. Okay, you've got this. You've got a funky looking function right there. Okay, and in order to figure out, so let's see, object of that is part of a system subject only to conservative forces. Okay, yada yada. There's our function. Okay, due to energy constraints, it can only move between -1 and 1. So what's the total mechanical energy of the system? Well, the if it can only oscillate between -1, okay, which is right here, and +1, which is right here, okay, then this is going to be, okay, um, all energy is potential at x equals -1 and x equals 1. Okay? So there, right, this is going to be -2, 3, 4, 5. So the total energy is equal to -5 joules. Okay? So right, this is the part right here. Like, so at this point, right, your potential energy, it's all potential. There's no kinetic. Okay. At the bottom, it would be, well, you still have, I guess, a little bit of potential, right? But everything is going to be potential right at this point right here. Okay. Object is released from rest at position -5 meters, moves in the positive direction, later passes position -1 meters. Okay. How does the object's speed change as it travels from -5 to -1? Okay, so for going from -5 to -1, you notice the entire time the slope is decreasing and it's getting steeper. Okay, that, I guess that's more for, sorry, that's more for acceleration. Okay, but since the potential energy decreases, okay, so PE decreases. Okay, so speed must increase. Okay, since potential energy turns into K, right? U turns into K as it goes. Okay. How does the acceleration change as the object moves? Okay. Well, the entire time, slope is negative. Okay. So A is rightward. Okay. And you can also think of it as towards lower potential. Do you remember when we were talking about the potential graphs in magnetism? Electrostatics, right? We were talking about the potential graphs in electrostatics, how we said it always points towards lower potential. Guess what? No different right here. Okay, no different right there. And then from, okay, x equals -5, okay, to x equals -1, okay, the magnitude of acceleration, okay, it should increase because it's getting steeper, okay, because it gets steeper. Okay, and the final part right here is that you've got another problem where you're given the position, right? You're trying to figure out the furthest position now. So again, I'm going to figure out the total energy here, okay? I can't just use the one from earlier because it's not the same problem, okay? Kinetic energy plus the potential energy. If it's at x equals 0, then my initial potential energy at 0, oh my gosh, it dips all the way down to -10. Okay. So then I'm going to do 1/2. The mass is 2. So that's just going to actually cancel this out to give you 1. So then you get v squared plus, or sorry, this is actually being minus, oh my gosh, I keep messing up here, -10. Okay. Oh, and sorry, v squared, I'm given v squared. That's 9 minus 10. So I should end up getting -1 joules, okay, for total E. Okay, -1 joules. Okay, so therefore I need to figure out if the total energy is -1, then I need to find out the 2 points right here. And so I've got -3 and 3. So the object, okay, oscillates between x equals what was it, -3? Yeah, -3 and x equals 3. Okay, so that's what you'd get for that. Oh boy, that was fun, wasn't it? It's like 5 pages of potential energy functions, but it was fun. We had fun the whole time, didn't we? All right. Well, peace out, Girl Scout. You got this.